Good day, dear panels and advisors. I am Miguel Lacson, together with my thesis partner, Hannah Lopez. We are glad to present our thesis titled as Energy Harvesting using an LTC 3108 circuit of stacked green chili capsicum inium plant microbial fuel cell. Plant microbial fuel cells, or PMFCs, offer a promising role as an alternative renewable energy source that has the potential to solve and minimize environmental issues. The PMFCs have been developed for electricity generation via biological interactions of microbes and plants using sunlight. In the rhizosphere part of the plant, there can be found exoelectrogenic bacteria that consume rhizodeposits, which generate an electric current. However, the disadvantages of PMFCs are it produces low power densities and it has inadequate performance in scaled-up systems. Hence, in order to test the capability of stacked PMFCs, the LTC 3108 circuit was utilized for energy harvesting in this study. The study aimed to determine the voltage, current, and power of individual and stacked PMFCs. The limitations of the study were: first, the setup was only done in a home garden setting. Second, it only focused on measuring the amount of energy harvested, and it did not focus on how to store the energy harvested. Third, the only design implemented in this study was the PMFC stake design, which would be shown in the methodology part. And lastly, the study did not consider the maturity and age of the plant. The objectives of this study were to investigate energy harvesting in PMFCs that were stacked in parallel and series. In this study, the voltage, current, and power of stacked PMFCs were determined. Lastly, was to evaluate if the energy harvested in the LTC 3108 was a viable alternative. In this study, 16 pieces of garden pots with a height of 6 inches, a radius of 6 inches, and an estimate of 9 liters of volume were used to house the green chili plants. Furthermore, the study used a 3D modeling design for the PMFC stake. The anodes and cathodes were printed using a protopasta, a conductive filament, while the separators were printed by a non-conductive filament. Figure 1 shows the actual green chili PMFC, and see that color black thing in circular shape? That is the actual PMFC stake design. Moreover, Figure 2 shows the appropriate dimensions in millimeters of this stake design. Both the anode and cathode are conductive, while the separator is non-conductive. The anode compartment was designed so that the water would flow there to reach the plant's root under the soil. In this study, the 16 PMFCs were divided into two setups, namely Setup A and Setup B. Setup A consisted of cells 1 to 8 and Setup B consisted of cells 9 to 16. Both Setup A and Setup B here were only stacked in parallel and series. As for the example, Figure 3 shows the schematic diagram of 16 cells in parallel connection, and Figure 4 shows the schematic diagram of 16 cells in series connection.
Good day, I am Hannah Lopez. Combination and cumulative stacking. In combination stacking, all 16 PMFCs were connected in 4 stacking configurations, namely the pure parallel series, and series parallel. Finding the stacking efficiency using cumulative stacking of forward and reverse order using the same 4 stacking configurations, and the cells were connected in permutation ways. From the schematic diagram here in figure 5, you can see that the first 8 cells are connected in series, and there is another set of 8 cells connected in series. Thus, when the two sets are connected into parallel, this becomes a series parallel connection. The forward setup that I have said earlier works in, for example, if I connect cells 1, 2, 3, 4, that is a forward configuration. While for the reverse configuration, you are connecting it with 4, 3, 2, and 1 cells. The polarization curve reading was done twice in the duration of the experiment period. One is for the finding the best resistor, and next is for finding the best stacking setup from the previous daily readings. This was executed by using different amounts of resistors, that is all the way up to 1.8 million ohms, and from there getting the voltage, and then afterwards calculating the current as well as the power. And from there you can now get the current and power density using the best voltage reading from the previous stack. As you can see here in figure 7 is a typical schematic diagram of a LTC3108 energy harvest circuit. This is the same as the one that we used, and you can see here what different components are used as well as where can we insert the wires needed in order to measure it from the PMFC as well as the multimeter. It was measured using the three wires that were connected from the multimeter to the PMFC. The V store, which is the V in, the V out, and the ground by connecting the V in and V out to the PMFC and the ground to the multimeter. For the data gathering, in the span of 2 weeks, we gathered both voltage and current for the different configurations.
In a week, the 16 individual PMFCs were measured. Every single PMFC showed different values of voltage and current. As can be seen here in figure 9, it has been observed that some individual cells do not have consistent performances. For example, cell 7 showed a high average value for voltage, but cell 15 showed a lowest average for voltage. Batalu et al. Stated that indeed, every PMFCs do not have the same performances as they have different bacterial activity, and this study setup did not share the same soil configuration. The plants may have variations in nutrient availability. In the study of Ramos et al., they observed in the rhizosphere that there are spatial and temporary heterogeneity in microbial activity. Since the said setup did not share the soil configuration, another thing that affects this was the soil temperature, which can influence the microbial activity and the root respiration of every single potted PMFCs. According to the study of Hashita et al., the performance of a single PMFC depends on several factors, which were the rate of bacterial growth at the anode, the formation of biofilms on the surface of the anodes as a result of various bacterial activities, and the decomposition of organic matter by microbes that are present on the surface of the anode. As mentioned in the methodology, the two setups, namely setup A and setup B, were both stacked in series and in parallel. Each individual cell of each setup was connected in various ways. The said connection consisted of 6 individual cells and displayed different performances. Starting in setup A, here we can see the performance of setup A as can be seen in figure 10A and 10B. In comparison, the parallel stacking provides the highest result of voltage. According to one of our references, stacking in parallel is a viable way to preserve voltage and prevent voltage reversal. Notice that one of the connections that provided the highest performance here in setup A consists of cell 7. Earlier, it was mentioned that cell 7 was the best performing individual cell. According to the study of Batalu et al., the performance of stacked PMFCs were dependent on the performance of single PMFCs connected at that specific time. Moving on setup B, the figure 10C and 10D provide the result of setup B. When we compare the two figures shown on the screen, the result was almost the same as setup A. This is because setup B has the best performance in parallel connection as well.
The cumulative stacking was done twice during the experiment period that helps in finding the best stacking efficiency that correlates between the amount of cells as well as the output of voltage and current. The readings were done as follows: series parallel, and parallel series, and divided into two in both forward and reverse configurations. This combines the different stacking that was said earlier, such as the individual and the stack. These are the first two trials made that has shown the best connection, which is 14 cells. And when comparing it to its theoretical and actual voltage, you can see that it varies in performance. Thus, the PMFC had exceeded its performance, and this is due to because of the idea of voltage reversal, which is why 16 cells is not the best configuration in this case. Here are the final two trials made. The only difference is that this C and D is done in a reverse setup. And as you can see here, it is lower in output when compared to the first two trials. This is due to its reverse connection that heavily affects the voltage and current flow in the PMFC, but the cap is similar at around 10 cells to the forward setup. The possible explanation results in the dip in performance as well as it's due to its lack of bacterial formation that causes the rate of growth of the plant to decrease. Thus the output of voltage and current decreases. Overall, the gotten graphs shown significant favors to averaging around 12 to 14 cells that was similar to the daily reading outputs gotten from the environment to the single cell. This creates an effect to the efficiency of the PMFC as a whole, which is why the forward and reverse configurations vary in results. For the polarization curve testing, the researchers have done 8 different polarization curves that consisted of the daily readings best output from the individual, stack, and cumulative testing that explored on what is the best configuration, which will be later used for the LTC period. And as you can see here in figures 13A and 13B, the best configuration is the pure parallel of cells 1 to 13 and 1 to 14. The trend for a typical polarization curve was achieved and had created similar results, except for figure 13A, which had a higher cap for all three axes seen here compared to figure 14A. However, their densities are comparable with one another, which is common. One of the trends seen here is the sudden power overshoot at around the lower voltage, which causes the unclear output that only happens at this low voltage output. This is due to the conversion of the power density at such a low voltage cap that is not seen at the higher output cap. However, this could also mean that the lack of microbial translation that I have said earlier had heavily affected the power output. Nonetheless, the issues are only minor and still attained a high density and shown the maximum potential of a home garden setup that was seen for 13 to 14 cells. Lastly, for the LTC readings, this was done at the final week using the best gotten stacking configurations, which was a forward setup in pure parallel for cells 1 to 13 and 1 to 14. The LTC was purely used as an alternative load and was connected, as said earlier from the methodology, using the VIN and Vout as well as its ground connection, as you can see here in figure 14. And since using a circuit, this creates a better flow of current yielding to an increase of 200%. The incorporation of the stacking studies had made the low energy harvest circuit a great alternative, since it had created comparable results to a typical PMFC, which this alone can be an alternative compared to a resistor. To prove as to how LTC had already been an alternative energy source, by proposing the setup of changing the power oscillation from its hardware had been done previously and can be applied here in the near future for PMFC studies. Finally, as you can see here in Table 1, which is the summary for all the gotten outputs, including the non-LTC period, as you can see here, the cumulative period peak for its voltage. And you can see here in the second week, which is the LTC period, had not shown its full potential, thus having a lower voltage. One adjustment that can be made in the near future in order to yield a higher voltage for the LTC period is by extending the experiment period. However, due to the lifespan of the plant, it was better to utilize it during the flowering stage at the end of its lifespan. This would yield its highest rise deposits, thus having a higher voltage and higher current output. Overall, setting the path now for using circuits that last longer and has more capabilities instead of resistors. This can be implemented in a much larger scale sooner or later, and with the given things that can be improved on, LTC had now proven itself to be a better alternative load rather than using the traditional resistor. As I have said earlier, this had made it into a viable alternative load. This poses a bright future for the PMFC to utilize the use of low energy harvest more, since this has proven to not only be better outputs of current, but as well as sustain outputs better than using traditional loads like the resistor. This can be applied in a much larger scale and can be improved.
For the recommendation, first, instead of using garden pots, it is suggested to plant the PMFCs with shared soil configuration. That would result in more precise results rather than it being more varied with one another. Second, due to the lack of time during the study's data gathering period, the cumulative stacking was done only twice a week. Therefore, it is recommended to perform it daily. Third, the LTC 3108 energy harvesting circuit was not used to its full capacity in this study. There are different tests that can be done as well, such as humidity test, power oscillation test, and etc. Lastly, the PMFC design can still be improved. One thing mentioned is the use of origami array to increase the stacking efficiency of the PMFC.